Welcome to the screencast that illustrates the first step for writing a variable coordinate proof. Up until now, all of the proofs we have done have been numerical proofs. In other words, you were given numbers for the coordinates of each vertex. When we carried out the proof, our conclusion was based on that specific figure. For instance, if I gave you the vertex coordinates for a specific rectangle and asked you to prove that the two diagonals were the same length, they might have been the same length for that specific rectangle, but it might not be a true fact about all rectangles. Maybe it was just a fluke that it worked out for that particular one. If we want to determine if the diagonals are congruent in all rectangles, we need to write a proof where the picture uses variables in place of the numbers for the coordinates of each vertex. In this screencast, we will focus only on setting up the diagram that we would use later on in the proof. This is an example of what you shouldn't do. Notice I've drawn a rectangle and I've attempted to give coordinates to each vertex. Notice how many letters I have. And also notice that there's nothing about the letters that would ensure that it ended up being a rectangle. I need to choose variable coordinates that ensure I have a rectangle, and a general rule of thumb is to use as few variables as possible. So as I just said, this is not a correct way to go about this problem. A better way to draw my rectangle is one of the corners anchored right at the origin. So other than being a little challenged using this new stylus, assume that that is resting right along each of the axes. So if I want to make that into a rectangle, I've got to give it coordinates. The coordinates of this corner are obviously 0, 0 since it's at the origin. This point right here is a certain distance over that we don't offhand know what it is. So I'll just give it a variable. Remember, I'm trying to minimize my number of variables. However, its height is going to be 0 because it's still on the x-axis. In a rectangle, the height is not necessarily equal to this distance across. So when I go to make the coordinates for this, I would say 0 for the x because it's not over at all, it's still on the y-axis, but its height, I have to choose a different letter than A because it's not necessarily the same size as A. So I'll call it B. And then finally, this set of coordinates over here, it's the same distance over as A is because of the fact that it's right up above A, and it's the same height as this point is. So its coordinates are going to be A, comma, B. Often there'll be more than one correct way to set up your diagram. I could set up my rectangle this way, where I take the rectangle and assume that I purposefully had the y-axis splitting the rectangle exactly in half. Notice this rectangle isn't anchored at the origin. So I would probably go about labeling my coordinates as some distance over, which I'll just call A, but with a height of 0 because I'm on the axis. If I've truly placed this thing so that the y-axis is centered on the rectangle, that allows me to know how to label this set of coordinates, because if I just went a distance of A to get to here, then I want to go a distance of A to go over to here. And in order to go A in that direction, it's going to make that coordinate negative. So negative A, comma, and again its height is still 0 because it's on the x-axis. To go ahead and put the coordinates here, its distance over is going to be A because it's lined up vertically with this, but its height is going to be some length that is not necessarily this length of A. So I'm going to give that a new variable. So in writing its coordinates, it's A units over, but it's some unknown height. Finally, if I'm going to go ahead and write the coordinates for this vertex, notice it's lined up with the negative a, so it's going to have negative a for its x-coordinate, but its height is the same as this point was over here, so it'll share that height. So the coordinates will be negative a, comma, b. If I were doing a proof about an isosceles triangle, again, there's more than one correct way to set up your drawing. I'm going to choose to move my triangle, my isosceles triangle, so that it's centered on the y-axis. I'm going to use the symmetry of an isosceles triangle to help me get the coordinate. Here I'm going to say that I have a certain amount of distance over that's unknown, but it's right on the axis. So what I'll do is I'll write the coordinates as some distance over, comma, the height of 0. Because of the symmetry of an isosceles triangle, I'm going to say that this distance right here is the same that this was, so it's going to be a, but in the negative direction. So the coordinates will be negative a, comma, 0. And since this distance up is not necessarily the same as this distance over, I can't use the same variable. So I'm going to label this as being 0 units left or right, the x-coordinate 0, but the height is going to be some value that, again, I don't know, and I need a new variable. The last figure that we're going to work with is a parallelogram, and that's perhaps the most challenging at first, but I'm sure you can get the hang of it. You could assume that I tried to get this to start right at the origin. It was just the imperfection of my drawing, but assume that that's anchored at 0, 0. So let's put the coordinates in. This right here is some distance over. We don't know how big it is, but we'll just call it a distance of a. But yet it's still a height of 0 because it's on the x-axis. Let's do the upper left-hand vertex next. If I want to write its coordinate, its distance over is not any particular distance that we've used before. So I'll give it a new variable, b. And the height of this point, even though it looks like it might be the same as the distance over, that was kind of an accident, and we don't know that it is the same distance over. So I've got to even give the height a new coordinate. So I'll call it BC. A fact you may remember about parallelograms is the opposite sides are the same length. So I have to make the distance we travel here be the same as the distance we traveled right here. You can tell by the coordinate over here that this length here was A. And since this point right here is B units over, the coordinate for all the way from here, which is B, then all the way a length of A, means that my distance the whole way is B plus A. Even though it looks kind of messy, B plus A, or A plus B, it doesn't matter which you write, would be the x-coordinate of that vertex. And as far as its height goes, its height is the same height as this point was. So we'll take the y value for that point and we'll share it with the other. So the second coordinate of this would be a C. That concludes this presentation on laying out a figure's coordinates before you try a coordinate proof. I hope this screencast was helpful.